Hello. What I'm going to do is review all the pre-calc material from Chapter 3. So I'll start with determining characteristics for a graph. We'll go through domain range, intervals, end behavior, and the min-max extrema stuff. And then I'll take a look at asymptotes and points of discontinuity. So that include like the holes in the graphs and then horizontal and vertical asymptotes. We'll go through different types of transformations, equations, and inequalities. So like, you'll see the greater than, which will be the dashed line and all the shading. So we'll go through a few of those, and then we'll go through just graphing a function and its inverse. And then using that same function, we'll determine the inverse equation and verify the functions are inverses of each other. And then we'll finish off with identifying critical points in a graphing calculator, and then discussing if a function is even, odd, or neither. So I'll get rolling with the first one, determining just characteristics of a graph. So notice both these arrows are going to keep pointing to positive infinity. So that means that my function will keep going to the left and keep going to the right. Therefore, my domain is all real numbers, or you could also say negative infinity to positive infinity is the open interval. The range values, notice I do have what appears to be a lowest y value, and that's because the end behavior of both sides of this function are going to end up going to infinity. So I'm going to end up with a lowest y value. So that lowest y value appears to be at -5. And since there is a point there, I'm going to put a bracket. So from -5 all the way up to positive infinity would be my my range values, and you can also say y is greater than or equal to -5. So that both explains that our range has all y values, basically from everything from positive infinity leading all the way down then to -5. As far as the intervals go, so I'm just going to work through both of these simultaneously, and again they kind of switch at the x values of all of our critical points then. So I really want to be focusing on all of these areas where the intervals stop and then switch, and it changes my function from increasing to decreasing. So my first interval is a decrease, and that occurs from an x value, all my values from -infinity leading all the way up to this x value right here, which is at an x value of -3. And then what happens is my function starts increasing. So from x values of -3 leading all the way up to my x values of 0, my function is increasing. And then what happens is it starts decreasing again. So from this little interval right here, which is x values of 0 to 2, so that's another interval of decrease. So this is the set that is in union with the x set of 0 to +2. And then what happens is from an x value of 2 leading all the way up to infinity, we would have it increasing again. So that last interval will be the interval from 2 to infinity. End behavior is where we're focusing on really where these arrows are pointing. So this one's going to go up and to the left, this will go up and to the right. So what we would say is as x approaches -infinity, so focusing on this arrow, as x is going to -infinity, notice your y values, your f of x values are getting larger and larger. This arrow is pointing up to positive infinity. So that's one of the end behaviors. And on the other end, as x approaches positive infinity, so as this arrow points to the right, notice that those f of x, the y values, are also approaching positive infinity. So those are also pointing to the right. And again, since your end behaviors are the same as far as both approaching positive infinity, that indicates also that I would have a minimum value in there. And that's where we're really going to look at these extrema, which are really just looking at your mins and maxes, and then identifying what those are. So I have a coordinate here of -3, -5. I have a point here that looks like it's at 0 and then 1/2. And then I have a point right here that's at, that's at 2, -1. So these are going to be my critical points. First of all, this one right here is the lowest of all low values that this function will approach. So that's going to be called an absolute minimum, and that is going to occur at -3, -5. And then what happens is a function increases and it stops here. That's going to be what's called a relative max. And the reason for that is because I have all these points over on these sides where I'm going to have y values that are greater than the y value of that function that has the y value of the half. So it's going to be a relative max, and that occurs at 0 and then 1/2. And then I also have this point over here, which is a relative min. and that 2, negative 1 is going to be my relative min because, again, it's not as low as the function goes. However, it is another one of those critical turning points where my function goes from decreasing to increasing. So that kind of goes through all the properties of that graph. Now we're going to identify algebraically where some of the points of discontinuity occur. So I'll start by just taking a look at this top function here. And what I'm going to do is expand this first. So if I were to multiply the inside of this, I would have x times x, which is x squared. And then I would have x times negative 1, which is negative x, plus 3x minus 3. So what I'd really want to do is distribute this 2 going across to this. And we could combine these inside terms as well. So I'm going to do that. Actually, I'll do that first. So really, I have a negative x plus 3x. So this inside is a positive 2x. So what I'm going to do is distribute that 2. So I really get 2x squared plus 4x minus 6. In my denominator, I have x squared plus 3x minus 4. And the reason I'm putting these in expanded form first is so I could compare my degree, which is the highest exponent of the numerator and the denominator. So since my degree is the same for both of these, I'm going to take a look then at the coefficients, which I have a 2 and a positive 1 on my coefficients. So what that means is that I'm going to have a horizontal, I'll just write HA, I have a horizontal asymptote at y equals, and all you do is just divide out the coefficients. 2 over 1 means that my horizontal asymptote is at y equals 2. Okay, and again, that was because my degrees were the same for the numerator and denominator. The other stuff that I want to do now is going to rely on me putting this into factored form. So my numerator is already factored for me, so that's just what's up there. And then the denominator, I'm going to look at two numbers that multiply to negative 4 that add up to positive 3. So that's going to end up factoring as x plus 4 times x minus 1. So now the next thing that I'm going to look for as far as my discontinuities go are if I have any common or repeated factors that are on my numerator and denominator. And it looks like this x minus 1 is a repeated factor. So what happens is algebraically this is going to end up being able to cancel on the numerator and denominator. However, there is the part where we want to identify where the hole is in the function, which means that it's going to occur wherever this x value will make this whole parenthesis thing turn to 0. So what x value turns my numerator and denominator into 0? And that is an x value of positive 1. So if I were to substitute 1 into both these parentheses, even all of this stuff, you would end up with 0 over 0, which produces a hole in the graph. So that algebraically could eliminate, and I would really be left with this for my function. And now I'm going to look for my vertical asymptotes, which is basically just looking at where the function is going to end up having 0 in the denominator. So what value of x would turn the denominator into 0? And that value is going to be at x equals negative 4. So these are my two asymptotes and my 1 point of discontinuity for this function. So what I'm going to do is save myself some room for the next one. Let me just delete some of this. And then I'm just going to get rid of this. So now I'm going to take a look at this function, which again, my numerator has a degree of 2 written right away, and that's in standard form. If I were to multiply my denominator out, I would really get x squared minus 6x times x minus 2. Now, I'm just going to take a look at this right away. I know my numerator degree is 2. So if my degree of my denominator is greater, I'm going to already know where my horizontal asymptote is. And that's the case here. Once I notice that I'm going to have to distribute this x squared across, I know that the degree of the denominator is going to be 3. So I already know, without even multiplying that entire bottom part out, I already know that my degree of the denominator is going to be 3. So since the degree of the denominator is greater than the degree of the numerator, that tells me that I'm going to have a horizontal asymptote at y equals 0. And that's always the case. I could have a function that says f of x equals x to the third over x to the fifth. And since the degree of the numerator is less than the degree of the denominator, you would have a horizontal asymptote at y equals 0. So that takes care of that part right away. The next thing I'm going to do is factor my numerator, and that is a perfect square binomial. So x plus 6 times x minus 6 are going to be my two factors, and then I'll just bring down the denominator. So what I'm going to look at next are those repeated, or should I say common factors of the numerator and denominator, which in this case is going to be x equals 6. So that tells me that we are going to have a whole then at the x value that would turn that into 0, and that would be positive 6. So if x were 6, I would have 0 here on the top, and I would have 0 on the denominator. And again, that's going to cancel out, and I'll be left on the numerator with x plus 6. And the denominator is going to be x times x minus 2. So the last thing that I'm going to do here is take a look at where my vertical asymptotes will be, and I'm going to have two of them. If x is 0, that denominator would turn into 0. Or, in this one, if x were positive 2, my denominator would also turn into 0. So my numerator, if x were 2, my numerator would become 8, but then the denominator is 0. And again, that's the reason why it would be a vertical asymptote and not a whole, is because you would end up with a number on top that's a non-zero number. So if you end up with 0 over 0, that implies that there would be a whole there, and that was the case with the 6. If I were to go back and substitute 6 up here, I would end up with 0 on the numerator and 0 on the denominator, and that's what's implying a whole in the graph. However, if you have a non-zero number divided by 0, that's where the undefined value comes in, and that's where the vertical asymptotes would occur. So now we're just going to do some transformations. So we'll start off with some key points analyzing each of the functions here. My parent function in this case being y equals the square root of x. So the square root of 0 is 0, the square root of 1 is 1, and the square root of 4 is 2. So I'm going to start off with these three values, these 3 points, and then we'll transform them. So within my argument of the function, I have a minus 3, which is going to horizontally translate my graph 3 units to the right by adding 3 to my x values. This 2 that's out front is going to act as a dilation, or a scale factor you could call it, and what's going to happen is it's going to multiply my y values to stretch this graph out a little bit. The parent function y equals the square root of x will look something like this. So what you're going to see is a stretched out version of that because of this dilation. The plus 1 that follows the argument is going to vertically translate my graph up 1 unit, and that's going to do that by adding 1 to the y coordinates. So all that I have to do is apply those little equations or expressions that are on the top here to each of my x and y coordinates, and that'll produce my 3 values for this graph. So 0 plus 3 is 3, 1 plus 3 is 4, and 4 plus 3 gives me 7. And then I look at the y values. I'm going to multiply my y's by 0 or by 2, and then I'm going to add 1. So this will turn into 1. This one would be 1 times 2, which is 2. Add 1, get 3. And then this value is going to be 5. So I'm going to plot these 3 points off to the side then. If I plot 3, 1, I'm going to end up here. 4, 3 is up here. And then all the way over at 7, and then up to 5. Okay, so what I'm going to do is connect this now, and again, it's going to be kind of an ugly curve. But notice again, my parent function were to look like this. So notice right away I don't start at the origin. I'm starting over 3 and up 1. And again, that's because of these 2 translations that occur. And then I have the dilation of 2, which stretched my graph out. This one will be an absolute value graph. So the parent function being y equals the absolute value of x, which standard V-shaped kind of graph with a slope of 1 in each direction. So what's going to happen here is I'm going to have a couple translations, and I'm also going to have a reflection. And also notice that this is an inequality, so I'm going to have some shading involved. So the points that I like to start off absolute values with are negative 1, 1, 0, 0, and the absolute value of 1 being 1. And we'll transform these 3 coordinates, and then we'll do our shading. So the first thing, within my argument, I have a plus 2, which is going to horizontally translate my graph to the left 2 units. This negative is going to make my y's go negative first before I add 3 to them, which is a translation. But the negative is what's going to reflect, so that tells me the V-shape is going to be upside down then. So I'm going to apply those characteristics before I look at the inequality part of this. So negative 1 minus 2, negative 3, 0 minus 2, negative 2, and 1 minus 2 is negative 1. So now I'm going to take negative y and then add 3. So negative 1 plus 3 is 2, negative 0 plus 3 is going to give me 3, and then the negative 1 plus 3 is giving me 2 as well. So now we can plot these points. So I'm going to go to negative 3, 2, negative 2, 3, and negative 1, 2. So I'm already seeing that I have this upside down V shape that's translated. And now I'm going to look at my inequality. So because this says greater than, or if it were to say less than, these would be dashed lines. If it had the greater than or equal to or less than or equal to, I would construct solid lines. But because they're dashed, that means that any point that's actually a part of that line is just not a solution to the inequality. And we have, first of all, so this is technically written with y first. So I can look at if it's greater than, it would be shaded above, and if it's less than, it's shaded below. So because this is greater than, I'm going to be shading all of this area, implying that every one of the points that are in this shaded region would satisfy that absolute value inequality. And you can always pick a test point to see if it works or not. So 0, 0 is always a nice test point. And the reason being is it would substitute 0 for the left-hand side of this equation. It also substitutes 0 for x. So 0 plus 2 being 2. And again, if you were to follow this, you would really end up with 0 being greater than negative 2 plus 3, which is 1. And that's just not true, which explains why 0, 0 is not within the solution. All right, the next one will be a cubic function. So a cubic graph is generally just going to have a curve that's going to look something like this with that point of inflection at 0, 0. And again, I have another inequality problem. So with the cubic function, I like to start with the points negative 1, 0, 0, and 1, 1. And we're going to transform these 3 points, and this is really just a translation too. Notice that there's no dilation or negative sign in the front that would reflect it or stretch it out or anything. So the minus 1 within the argument is going to add 1 to my x coordinates. The plus 2 that follows that is going to add 2 to the y's. So I'll just follow these translations for these 3 coordinates. So negative 1 plus 1 is 0, and then I'm going to have 1 and 2. And then add 2 to the y values. Negative 1 plus 2 is 1, and this will be 2, and this will be 3. So what I'm going to do is plot these 3 points. I have 0, 1, 1, 2, and 2, 3. And really, I mean, it looks like you could just connect them with a straight line, but just knowing the behavior of a cubic function, again, realizing that the parent function here is y equals x cubed, it has that curvy shape. So I'm going to now look at the inequality that it says less than or equal to. The or equal to part indicates that I can have a solid line drawn through this, and this is really what the curve is going to look like, and that it's less than or equal to, I'm going to shade everything that's going to be underneath this curve. So every one of these points. In this case, it does look like 0, 0 would be part of my solution, and that would end up working. Alright, so next one we're going to graph a function and its inverse, so I'll do the same thing. Starting with the transformation process. So this function is a quadratic, so I have y equals x squared being my parent function, and the inverse function then is going to be a square root function because these two are inverses of each other. So first of all, even the the squared quadratic function is going to produce a parabolic graph. And then if I were to look at the square root graph, it's going to end up being kind of a sideways version of that. And again, really what this comes down to is that notion that all inverses are just reflections over this green dotted line, which is y equals x. So if you were to take this black parabola that I have and flip it or reflect it over the green line, you would have the blue graph, which is going to be the square root function. So what I'm going to do is start with my points that I normally use for quadratics, which are negative 1, 1, 0, 0, and 1, 1. And I'm going to first do the transformation of this, which is just the stuff that we did. So the x minus 3 is going to add 3 to my x coordinates because it's within the argument. The 2 is going to serve as a dilation, so it's going to multiply my y coordinates by 2. And that's all I'm going to do. There's no vertical translation in here. We just have the dilation. So negative 1 plus 3 is 2, 0 plus 3 is 3, and 1 plus 3 is 4. And then I'm just going to multiply my y's by 2. So both of these are going to become 2, and this is going to stay as 0. So we'll take a look at what those points will be, and I'll kind of stay with the same colors here. So I have 2, 2, and then there's 3, 0, and 4, 2. So notice that I have my parabola being kind of stretched out, and that's because of that dilation. So it's going to make the parabola narrow, really, and that is my f of x function. So now all we have to do to get the inverse coordinates are interchange or flip-flop your x and y values. So to get my 3 inverse points, which will be my inverse coordinates, 2, 2 is actually going to become a part of both of those, but this point is going to be at 0, 3, which is on the y-axis, and this will be at 2, 4. So we'll take a look. My 2, 2 is here. I have 0, 3, and then I'm going to have 2, 4, which is up here. And what will actually happen on this graph then is it's going to have that sideways kind of curvy shape. It looks like a sideways parabola. And again, that's going to be my inverse function, f inverse of x. So at the end of all this, what you should see then is going to be a reflection over this line, which again is y equals x. That goes through here. So if I were to take the red function and just flip it or reflect it over that line, it would turn into the green function. So what we're going to do is kind of extend onto that and look at the equation of an inverse function. So if I were to even go back to this, notice that what the next question is asking us to do is write the equation, oops, why did I just do that? Write the equation of the green curve in this case. So if I were to kind of undo a bunch of those points here, oops, redo those points, I really just want to know what the equation of the green curve would be in this case. And that's what we're going to be solving for in the next part. So in order to do that, there's a few steps we can follow with inverses. The first thing I'm going to do is change my f of x to say y equals, and then I'll copy the rest of my function down. But really going back, by definition of inverse, my y equals x equation, the line y equals x is what we're reflecting over when we're doing inverses. So what I'm going to do is interchange my x and y values here first. And now what we really just want to do is isolate the y. So I'm going to first divide both sides by 2. So I'm going to end up with x over 2 equals y minus 3 squared. And this is where the inverse function really comes in for the parent function. The square and the square root are inverses of each other. So now what I have is the square root of x over 2 equals y minus 3. And I have one more step before isolating y. I'm going to add 3 to both sides. So what I really end up with now is y equals the square root of x over 2 plus 3. And the last step is to just write it as f inverse of x equals instead of y equals, and bring the function over x minus 2, or x over 2 plus 3. So these are the functions that are inverses of each other. And we're going to verify now that they're inverse using composition. So I'm going to show you a composition, which is a fancy way of saying I'm going to take one function and just substitute it into the other for x. So I'm going to take our inverse function and I'm going to substitute it in the original function for x. So what's kind of unique about inverses then is they really just undo each other. So if I were to say pick an x value and add 2 and then multiply by 3 and then add 1. If I wanted to work backwards, I could subtract 1, divide by 3, subtract 2, and you would end up right back to where you started, which is x. So that's what's going to happen in this case, is if our functions are inverses of each other, you're going to end up having a composition f of f inverse of x is going to just come out to x, which basically means all of our operations are going to undo each other, and you're just going to be left with whatever you started with, which is your x value. So I'm going to do that in this case. Again, I'm going to take f of f inverse of x. So I'm going to take my top equation here, and again, I'm going to rewrite it, except in for x, I'm going to substitute this blue box, which is the entire inverse equation, the square root of x over 2 plus 3, and again, that all went in for x. So now I'm just going to write the rest of this down, which has the minus 3 and then the squared. So this is what I end up with. Now I'm just going to start eliminating or crossing off certain things that would be inverses of each other. So the 2 is going to get brought down. The square root of x over 2 is going to come down, but the 3's are inverses. So I have a positive 3 and the negative 3 here. So that's going to, I just kind of cross them off. Those will eliminate. The next thing is I have the squared and the square root. So these are inverse functions, the square and the square root. If I eliminate those, I'm now left with 2 times x over 2. And the last thing here would be the 2's eliminating each other. So again, I am left with x, which verifies that my functions are inverses of each other. And that leaves us with the last one. So what we're going to do is graph a function in the graphing calculator, identify the critical points, and then prove if the function is even, odd, or neither. So I'm going to pull up the graphing calculator, and I'm going to go to y equals, and we'll type this in. So I have 2x to the 4th power minus 6x squared, and then plus 1. And what I'm going to do is press zoom, and then I'm going to press the number 6 just to get a standard window. And I can totally see my function within that window. It looks like, as far as the end behavior goes, it's going to keep increasing on the left-hand side and approach infinity, and same for the right side. As x approaches positive infinity, your f of x will also approach infinity. So what we're going to look at are the critical points within this. So it's kind of tough to see. So I'm going to really just zoom into this area that's up here. So I'm going to reset my window to be -5 to 5 in all directions. And it's going to allow me to kind of visualize some of these mins and maxes a little bit better. And you don't have to have the same exact window as mine, but you know, the same picture. So again, there's just kind of a close-up of this function. So we'll really just discuss the properties first. It looks as though I have two mins that are equal, which means these will be considered absolute minima. And then I'm going to have this relative max point up here. So what I'm going to do is figure out what those points are, and I'm going to press second and trace, and I'm going to first get my minimums. So what I'm going to do is take a look at this one that's on the left-hand side. So I'm going to go somewhere to the left of the curve first, or to the minimum first, and then move over to the right-hand side, and hit enter, and then go back to the middle and press guess, or press enter for guess. And that's going to give me my minimum value. So I have an x-coordinate of -1.22 and a y-coordinate of -3.5. And again, that's going to be one of the absolute minimums. And that is going to be my other point as well. So if I were to go to the other side, again, second trace and go to minimum, and do the same thing on the other side of this. So the parabola is going up and then down the other side. If I make my left bound here, and my right bound on the other side of this, and then kind of just trace back to the middle for my guess, it's going to give me positive 1.22, but also, again, that idea that it's at -3.5. So 1.22 and then -3.5. And again, those are both of my absolute minima. Again, because the function will not get any lower than those. So what I'll do is go back and do second trace, and this time I'm going to look for the maximum, which is the fourth option, and we're going to try to find what this point is. That's right in the middle of our graph, and it's going to be at 0, 1. It already looks like that, and that is what it's going to be. So do the same process. I have my left bound, I have my right bound, go back to the middle of this, select enter, and there's my maximum. So it's a relative max. It's not an absolute because the function will get larger on both sides. So this is an absolute max at the point 0, 1. Or I'm sorry, relative max at the point 0, 1. And the next thing we're going to do is algebraically and graphically prove if the function is even, odd, or neither. So I'm going to just make a rough sketch of this really quick. I have this point that was at 0, 1, and then I have my other critical points, which were my absolute minima, and those were somewhere about right here and right here. So what we noticed is my function was increasing on one side, and then it came up and right back down, and kind of formed something like this, which that just looks ridiculously ugly. But really the shape of the graph is all that I'm looking for. So to determine graphically if something is even, odd, or neither, you want to look for symmetry. So if the function is symmetric over the y-axis, if it looks like I can fold my function over the y-axis, that is going to be an even function. And that is the case here. It totally looks like I can take any point that's on the left, reflect it over the y-axis, and get that equal point on the right. And that's what we see here as well. Notice that my x value of -1.22 has a y value of -3.5. And the x value of positive 1.22 equals -3.5 as well. Algebraically, that means that all the values of my function f of x would be equivalent to the function f of x values for f of -x. So this is basically saying all of your y values for a positive x value would be the same exact y values for the negative version of that. So if I, for example, took f of 5, that would give me the same y value for f of negative 5. Something like that. And that's again what we see here, and that's the point of that symmetry. If it were an odd function, you would see symmetry around the origin, and it would look like a rotation of 180 degrees about the origin, and that would indicate that it's an odd function. Algebraically, for an odd function, f of x would equal, f of negative x would equal negative f of x, and we would be substituting those values in. What I'm going to do is algebraically show for this function that, again, that it's even, and I'll do it algebraically just to prove that it's even. Here's my function f of x. What I'm going to do is prove that that is equal to f of negative x. And again, that would just imply that the function was even. So I'm going to replace my x's with negative x's and simplify. So it's the idea that in this case, in all cases, any negative value raised to an even power is going to come out even. So I'm still going to end up with 2x to the fourth. This negative x times another negative x would still give me x squared, so minus 6x squared, and then my plus 1 would come down. So the fact that this equation matches this equation, the fact that my f of x equals f of negative x, proves algebraically that the function is even. Again, if my f of negative x were to equal negative f of x, then I would end up with an odd function. So that's not the case here. We wanted to focus on an even function, and again, graphically it was symmetric over the y-axis.